Hello everyone. This video is going to be about how to download topographic data in Google Colab and how to manipulate it with something called gdal. The data we're going to get is from opentopography. Opentopography is this amazing resource where you can get all sorts of topographic data. If you want to get the full power of opentopography, you need to get an account with them. So you can get that by clicking on My OpenTopo. And there's also this little button here that says Request an API key. So the way I'm going to get the data that I'll use for today's example is through this API key. I'm going to use a notebook that I've made. So the notebooks can be found in my GitHub page. You can see the website up here. And I'm looking at this one in SMM Teaching Notebooks, Basic Topography, and Lesson 1. So this notebook is based around a course that I teach. So if I click on the Open in Colab button, it will open an instance in Google Colab. And I've done three things first because they take a little while. So the first thing, the way I download data, I use a little wrapper that's built into a Python package that I wrote called LSD VizTools. I wrote this along with a few others. And then I need to install gdal using something called conda Colab. So you just need to run this next cell. So these two steps will take, 20 seconds. And then we install gdal and another package called proj. And I've just put in one of my software packages for good measure, but actually we don't use it in this notebook. So we just download gdal and proj. That takes about a minute. So those first three steps will take about a minute and a half, and you need to do that every time you start a Colab notebook and you want to use these tools. The next thing is in Google Colab, there's a little bit of a bug. gdal doesn't know where a library is. The library has all this geospatial information, so it helps gdal understand where in the world your topographic data is. So you just need to execute this thing. If you don't execute this little thing, it will break. Okay, so the first thing I'm going to do is I'm going to get data from opentopography. You can go onto opentopography, click on data, go through the data catalog. So there's tons of LiDAR data sets in here. You could go into the data catalog. You could look for global and regional DEMs. They've got all sorts. So there's reference model of Antarctica, the Arctic DEM, and then all these global data sets. They all have these little names through here. All of these are accessible through an API interface. So you could download them here through a kind of web interface, but I've got a wrapper for the API interface. Now, the API interface requires an API key. So you've got to get the API key and you keep it in a file. You shouldn't show anyone your API key. So I just have made a text file containing my API key. I've called it the specific thing, my OT API key.txt, and then I drag and drop it into this session of Google Colab. Google Colab, in your sessions, it doesn't store files. So once you close out this window, all those files will disappear. Okay, so that's there now. The next step I'm going to do is I'm going to grab some data. And I should say that, so these two steps are not required if you're in Google Colab. That's if you're in a different environment at my university, University of Edinburgh. Okay, so first, I do need to import some stuff for this lesson. So what am I importing? I'm importing some standard Python packages, NumPy, but I'm also importing a few things that allow me to look at raster data and download raster data. So let's grab the data. How do you grab the data using my little wrapper for the OpenTopography API? Well, all you need is the lower left and upper right corners of your area that you want to select. So these are the latitude and longitude of these. How do you get those numbers? It's very easy. You go on a web browser, go into Google Maps, and if you right-click your mouse anywhere, it will give you the lat and long, and you can click on that and it'll copy to your clipboard, and you can just paste these numbers in here. So it's very quick and very easy to get locations. I've pre-selected the locations. So I'm just gonna, if you want a different place, you just put in different lat longs. Again, get them from Google Maps. So I'll execute that. Now, the next step, this looks like a lot of code, but you will never ever change this code. Well, you might change the code a little bit. You might change the name of your file if you wanted to have a different file. And you might change the data source. So in this case, I'm using the Copernicus 30 meter global DEM. There's lots of different options here. So I've written some of them down, but you can see all the options at opentopography.org. So in this case, I'll just click go. And what that does is it goes into OpenTopography and it grabs the data. Now it will take a little while it downloads, and then it's done. It took 11 seconds. Okay, so we want to look at the data. When you're in a Colab session, you've got a Linux operating system sitting underneath. So you can do things like look at the files in the Linux system with a command line. So anytime you call the Linux system underneath, you use this exclamation point. And we sometimes say bang for that exclamation point. So you would type bang ls. So I do that. And this is what's in my this session, all the data. So I've got my API key. This is the DEM I just downloaded. This is something that always comes with a Google Colab thing. You can click on this little file thing, and all that stuff is here. So there's a kind of your typical graphical file system here. But if you work with topographic data a lot, you are going to end up doing command line stuff. So you'll look at data this way. So this thing is what I just downloaded. Actually, I've changed the name. That's Copernicus 30. The last time I did this was using SRTM data. So we've got the Copernicus 30 version of this data. I should say if you download from OpenTopography using the web interface, you won't get the TIFF file straight away. You'll get a zipped file. So there's other lessons about how to deal with that you can find in videos. Now the next thing, we're going to actually use this gdal package. gdal stands, I'm not sure if I said this already, it stands for the Geospatial Data Abstraction Library, which is a mouthful. But once you've installed it, you will get a bunch of command line tools. One of them is called gdal info. So when I say command line tools, they work from a Linux command line. Again, to call the Linux command line, you put an exclamation point in front. And again, I sometimes call that bang. So you'd say bang gdal info, and then you would type in the name of the file you got, which is the one I just downloaded. So let's see what is in here. gdal info tells you all you need to know about the raster you just downloaded. Okay, what is in here? It has the driver, so that is what kind of file it is. This is a GeoTIFF. It tells you how big it is. It tells you all sorts of complicated information about the ellipsoid, the kinds of the geographic projection, and all sorts of stuff. You don't need to really know what this stuff is, but if you get some kind of problem with your data, you might use gdal info and see if you've done something weird in here. You have to probably have worked with geographic data for quite a long time before you start to recognize errors in gdal info information. But here it is. This is how you learn all about what the geographic projection is in here. Okay, I included in this notebook a bunch of explanations of what all the information is. So can we look at this data? There's a lot of different ways to look at this data. There's a Python package called rasterio for raster in out, or Rio. Sometimes we shorten it to Rio, but the name of the package is rasterio. So you can open these files using rasterio. So let's just open the file and look at it. So you'll see when you use rasterio to open it and you look at the metadata, so you can look at the metadata in a rasterio file, it's kind of the same stuff that's in gdal info. Okay, next we can do things like print to the screen the kinds of things that we see here. So this is CRS. Sometimes you will hear GIS people talk about a CRS. That is for Coordinate Reference System. And that is actually quite important. So I'm going to go up here. Coordinate Reference System. There are many different flavors of coordinate reference systems. If you get the coordinate reference system wrong, you will have a terrible time. Many of the errors that I get from students are because the coordinate reference system is wrong. I use topographic data so much that I have memorized various coordinate reference systems. Coordinate reference systems use something called an EPSG code. The most common global reference system, so it's called WGS 84 reference system. The code for that is 4326. So that is a very common coordinate reference system. I'll probably introduce other coordinate systems in later videos. However, converting between these coordinate reference systems are going to lead to a lot of errors, so you need to know what EPSG code is and your coordinate reference system. So can we also look at the raster? We can use a simple function in raster.io. So this thing can make a plot of the raster. It's a very simple plot. So you've got X and Y coordinates here with numbers. These are just the row and the column. So it's not telling you anything about how far anything is away. That's just the row and the column in the raster. What if we want to look at the hillshade? So gdal also has a bunch of tools that are wrapped in a little package called gdal-dem. One of them is to make the hillshade. So if you make the hillshade, you put in the name of your raster, you tell it what the raster out is, and I systematically call my hillshades the same name of the raster with _HS. Then you can designate an algorithm for creating the hillshade, and there's this Zevenbergen-Thorne algorithm which just looks better than other algorithms. So if I were you, I would always use that algorithm. Okay, so what that will do, that will have made the new raster. Here, I'll look in the file format, and then there's that hillshade raster that just got made. And finally, we can look at it. So there's the hillshade of this raster. It looks a little bit funny, and in lesson 2 of these notebooks, I will explain why it looks funny. I will give the punchline now because perhaps you won't watch the next video. If you don't watch the next video, the reason why this looks funny is because the vertical units of this are in meters, but because this is a geographic coordinate system, so that means it's on a sphere, the pixel size is in decimal degrees. So where you are in kind of X and Y locations, it's not X and Y, it's latitude and longitude. So the pixels are very, very small. 0.0002, or well, it's nearly 0.003 decimal degrees. So the horizontal coordinates are very small. The vertical is bigger. So that's in meters. So you get something that looks like it's got tiny little pixels and very tall mountains. So to fix that problem, you need to change this to a different coordinate reference system, something called a projected coordinate system, where you project it onto a flat plane. And we're going to talk about that in the next video.